Morning, everyone。好，在今天直播前的话，我想，我先跟大家稍稍介绍一下直播的形式。那直播的话，大部分当然还是比较单向的，但大家不用太害怕，它其实就只是一个荧幕可以切来又切去，切来又切去，就是好玩的室内摄影棚这样。那我在一个非常非常阳春的摄影棚，这样只有我一个人操作所有的仪器。所以，如果在整个直播的过程，你发现影音有任何的问题的话，都请你直接留言给我看，那我会及时看一下。那我想我们彼此也适应一下下，因为这个毕竟用直播来上课，其实当然是一种尝试。那我以前因为好奇，其实也玩过一阵子了，所以稍稍跟大家讲一下。那在我们接下来就是疫情比较严重这一段时间嘛，我想大家也就不要彼此耽误，变成就是说，哎，有人确诊，然后我要隔离，或我确诊你要隔离，然后就大家这样互相循环下去，可能最后人生都在隔离中了这样。那所以我们就转换另外一个弹性的形式，那也跟所有的助教讨论过了。那所以他们的演习课，我们也特别为大家开了一个线上的一个云端的一个讨论室，那也请大家可以进去。那我们目前其实演习课云端的会议室的话是用 Zoom 的服务，那大家其实不要太惊恐，这个 Zoom 的服务我采买的是借由它所有的伺服器，其实事实上都是在日本哦。并不会有任何治安上的疑虑，请大家特别的放心，好吧？那接下来的话就稍微跟大家讲一下，就如我之前有跟大家在信中讲，那因为这门课是英语授课，所以待会等我们真的进视到正式的学习内容的时候，我还是会用英文讲。那你在过程底下，其实你可以用英文或中文提问，通通都可以这样。然后，如果你用英文提问，我就用英文回答；如果你用中文提问，我就用中文回答。如果我待会上课上的太嗨到，一时忘记了，看大家的留言的话，那怎么办呢？那好像也没有办法哈。那我最后的话，其实还是会留一些好玩的东西。那也希望大家YouTube 的影片，大家知道，就直播完之后，它其实需要在平台上整理好几个小时，所以可能隔大概半天多，它才其实会重新再上线，所以不用到太害怕。重新再上线之后，我们的聊天室我选择其实是让它可以重放的。那我提出的问题，如果大家有什么有什么兴趣或者说想要留言的话，哎，就可以留在下面留言的地方，然后继续讨论。那我们来看看说这样的一个上课的形式，哎，会不会其实也有不错的一个效果出来？这样，So we're going to start our lesson today. Okay. So today we're going to talk about something rather interesting. So as you can see in this figure here, okay. So that's the vector operator, the del operator. Or sometimes it has a pretty interesting name called nabla. And I would encourage you to look it up, that what nabla means. So with this vector operator, hence we can do differentiation. As you learn in the calculus, we just generalize it a little bit. Or on the other hand, once you can do differentiation, we can also do its inverse operation, integration. So today we're going to go over the gradient that we have talked about, and we also have a brand new understanding about divergence. That is how the field flows out, and the curve, how the field rotates. On the other hand, on the integration side, then I would introduce the line integral, the surface integral, and the volume integral. In comparison, the differentiation part is going to be more challenging, and I do hope that you will keep your attention and efforts at the very beginning of the video. Okay, so let's start and see how it goes. So to warm up, let me just go over to the previous explanations about the volume element in cylindrical coordinate and also in spherical coordinate. Okay. The nice thing about using YouTube Live is that I can be casually drinking tea without any constraint. So it's wonderful. I hope that's also wonderfully for you, that you're probably still lying in bed, turning on your cell phones and things like that. So this is a cylindrical coordinate. As you can see here, that this little cube here has a scaling factor that is 1. A scaling factor here is also 1, and scaling factor here, the only non-trivial one, is rho. So keep that in mind. So that's the cylindrical coordinate, which is relatively simple. Let's just move on to the spherical coordinate. For the spherical coordinate, this little cube volume is slightly more complicated. In the radial direction, in the radial direction, the scaling factor is 1. On the other hand, in the theta direction, the scaling factor is already non-trivial. It's r times theta. That means it has an r dependence. And in the phi direction, this is the most complicated one that we explained before, that it has a scaling factor with r times sine theta times d phi. And with all these scaling factors, now you can just describe how the volume elements can be expressed in terms of the differential of the coordinate. So we call out the Mr. Q, that is the little cube that we just described. And so in each dq1, dq2, dq3, you got different scaling factor h1, h2, h3. And in this perspective, you can then have a coherent understanding about different curvilinear coordinates. And I think this is really nice. So please do try to pick up this more general concept. That is, in Cartesian coordinate, you have this Mr. Cube in its simplest form. Its edges are nothing just but dx, dy, dz. That is, all the scaling factor are 1. But for cylindrical coordinate or for spherical coordinates, this tiny little cube still works, except it has non-trivial scaling factors h1, h2, and h3. So that's it. So of course, from this figure, it should be straightforward to see that this volume element is nothing but h1 times h2 times h3, and then a product of dqi. So that is the material that we have learned in the previous lectures. And marching with this knowledge at hand, let's just march forward to the gradients and divergence and curls today. So let's see how it goes. Yes. So here is the gradients. By definition, gradients is gradients satisfy this relation. That is, if you move a little bit in the space, it will cause the scalar field to change a little bit. And the differential of the scalar field, which of course is a scalar, is related to the differential of the displacement vector, which is a vectors, by gradients. Okay, so that is the geometric definition of gradients. And with this, it doesn't really depend on any coordinate at all, right? So that's how the gradient is defined. That is, a gradient is defined so that its inner product with the little tiny total differential of the displacement operator is the total differential of the scalar field. Okay, so once you got that in mind, let's try to see how we can derive the gradients in terms of components in general curvilinear coordinates. Okay, so again, using another identity, that we also know that d phi can be viewed as a function of q1, q2, and q3, and thus you can take partial differentiation that d phi dqi times dqi, and I is from 1 to 3. And this is an identity in a sense is that you can just manipulate it with different settings. So let's do the first one. Suppose now if I do dq2 and dq3 equal to 0, okay? That is that I'm holding q2 and q3 constant. And in this sense, if I then ask, how do I move forward in this location? And why do we want to do that? It's basically by different settings we can trace out the edges of the Mr. Q. So here we are tracing out the edge along the dq1 not equal to 0 directions. So according to the partial differentiation we learned, this is dr dq1 times dq1. But as we previously know that this dr dq1 is the base vector a1 along the first directions, and it can later be written as the scaling factor h1 times e1. Okay, so combining everything together, you found this very interesting thing. The displacement change with h1 dq1 along the e1 directions. So that is the first geometric relation we got for dr. And of course, we can trace out dr in the dq2 not equal to 0 direction and dq3 not equal to 0 direction, which then I will just leave it as your exercise. Okay, and so the result is actually going to be very, very simple like this one. So let's move on. Once you got this at hand, how can we manipulate and try to rewrite d phi? Well, first of all, this d phi and gradient phi is gradient phi dot dr, right? But since dr here can be written as h1 dq1 times e1, so I'm just going to move this here. And once you move it here, you then realize, oh, so you got a gradient phi dot e1. And then h1 dq1. That's coming from the definition of the gradients. But on the other hand, from partial differentiation, we also know that d phi is nothing but its partial derivative with dq1. Thus, you found one expression from the geometry, you found another expression from algebraic manipulations, and they of course are the same. So then you got this very beautiful result. That is the projection of gradient phi along the first direction is nothing but, well, see, here you got this one here, right? Here you got this one, and they must equal to each other. So we just shuffle the scaling factor over here, then you got this. And this is really cute. What does this mean? It means that gradient phi, the component of gradient phi along the first direction, is not just d phi dq1. It acquired an additional scaling factor, or to be more precise, a reciprocal of the scaling factor, 1 over h1s. And one can repeat the calculations for the second direction, for the third direction, and then you will get the gradient phi in the first direction got a correction of 1 over h1. In the second direction, you got 1 over h2. In the third direction, you got 1 over h3. And this is not that surprising, to be honest. If you really think about what is the partial differentiation, it is really just the change of phi divided by the change of the length, right? And so, if you really come back here, it's almost as if that you should divide, instead of dq1, you should divide it h1 dq1. That's the wisdom that we got from this very simple Mr. Cube analysis. And so that's why that here you get 1 over h1 here in the denominator, okay, not in the numerator. And so, okay, once you got this, it's relatively simple. We can, since this works for all fields, sometimes we can just pull out the scalar field and write this in just more abstract vector form for the del operator. So then the del operator in curvilinear, in general curvilinear coordinate can be written in terms of 3 components. And the correction is almost trivial. It's just that instead of having like ddx, ddy, ddzz, now it's ddq1, h1, ddq2, 1 over h2, and ddq3, 1 over h3, and that's it. So that is the part of gradients. And so let's go back. Since this is video, so it's really nice because if you get confused later on, you can pause me. And if you really think that this part is trivial, you can fast forward me. Okay. And if you find my English is pretty poor, that's a cancer. There's no cure for that. Sorry about that. Yeah. I don't really think that you can Google translate my video at this point. You can donate captions, Chinese and English captions. That would be very welcome. So what exactly have we done to achieve a very cute formula like that? It's really coming from this very simple relation of gradients. And that's actually the geometric definition of gradients. And also this trivial identity of taking partial differentiation. As I emphasized many times, try to really understand and capture the notion of total differential, which is really important in many applications. Okay, so do not get satisfied by knowing how to calculate partial derivatives. These are relatively trivial, but try to really capture the notion that how you can actually compute total differential. Great. So far so good. Any questions about the gradients at this point? I only see good mornings in the chat room, so that's great. So let me take a little pause, drink some tea. Then we will move on to our next subjects. Our next subject is divergence. And what exactly is divergence? So later on, we will prove a very important theorem. But here, we're going to just call out the Mr. Cube and have a refreshing understanding about divergence. So what exactly is divergence? Divergence is defined, its geometric definition is rather simple. If you want to calculate the divergence at some particular point, let's say particular point, you just call out a Mr. Cube. You calculate the flux through the 6 planes and then divide it by the total volume, and that is the definition of divergence. So a divergence is a really pretty cute way of how you measure the field diverge from one point. Okay, so if you have a source, then the vector is flowing out. If you have a sink, then the vectors are flowing in, and both will give you a non-negative, non-zero result. On the other hand, if there's no source, there's no sink, then your inflow and your outflow will equal to each other, and thus the net flux is 0 and the divergence is 0. Okay, so that is our understanding. I'm sorry, somehow I'm speaking English, but I think I just triggered my iPhone. Let me do something to it. Okay. Okay. So let's go back to the divergence. And so with that said, if now we try to calculate the divergence, it's relatively simple. You just call out Mr. Cube and calculate the flux. And then you know how to do this, okay? So here, let's calculate the flux along the Q1 directions again first. And so here, this is flowing outwards, this is flowing outwards. And so how are you going to calculate that? Well, rather simple. Think about this. You have a flux, right? Let's say J here. And you have an area which is H1, H2, dQ2, dQ3. Okay? And so you write it out. What that means is that you just multiply J1, H2, and H3 at this location here. This location is Q1 plus dQ1. And on the other hand, on the opposite side is pointing in this direction. That's why there is a minus. So you subtract that. And on this surface, again, it has a J1 and it has H2, H3, and dQ2, dQ3. You might rush to the conclusion that saying that, okay, so it is 0. Not really, right? Why? Well, because J1, H2, H3 is at Q1 position and at Q1 plus dQ1 position may not have the same value, right? As I mark here. And in fact, their difference can be computed by partial differentiation, right? Because the other two coordinates are kept constant. The only difference between these two planes is Q1 and Q1 plus dQ1. And thus, their difference, this term here, is nothing but the partial differentiation of this whole product times dQ1, as we learned before, right? So the difference is the partial derivative times dQ1. And so then you end up with this one. So it's really, really cute. You found that by calculating the flux through this Mr. Cube, you got dQ1, dQ2, dQ3 automatically. And try to be really, 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 really careful. We are taking partial derivatives with respect to the triple products J1, H2, and H3. The reason is the following. Think about this. The flows, the flux can change due to several reasons. The first one is that maybe the J's take on different values when Q1 is not the same, right? So that's why you have a J1 inside the bracket. But on the other hand, remember that this H1 and H2 and H3s can also change with coordinate. We are not living in Cartesian coordinate anymore, right? So there might also some change due to H2 and H3 in this case. That is the area change. And flux is the J times the area. So of course, the change can due to J can also due to area. And that's why that we multiply them together. Okay, so try to keep this in mind. That is, in general, curvilinear coordinate. This H1, H2, H3s can always can all depend on the coordinates, and thus it will change. They are not constant. Okay. So flux along the Q1 direction, the pair of planes in the first directions we have computed is like this. We can of course then compute it the other pair in the second direction, in the third direction, and you just add these contributions all together from basically 6 planes, and you will get in the first direction, in the second direction, in the third directions. Once you derive this whole thing, sometimes when you get the answers, you see the symmetry and you know that this has got to be right. And you found this is actually right, right? So this is the J1 component flowing through the perpendicular directions of the plane. And thus is multiplied by H2 and H3. And all three comes together and give you 1, 2, 3, right? It's just JHH. While here, you also got the component 1, 2, 3, except now you're using J2. And here again is 1, 2, 3, and you're using J3. Okay, so this form is actually relatively simple once you have really sit down and derive it. So that is the total flow, total flux through this Mr. Cube. And of course, we can then divide it by the volume. Then we got the divergence, okay? And so try to remember that this volume here is not just divergent J times dq1, dq2, dq3. It got this correction. It got this correction, so be careful, okay? So now you got H1, H2, and H3. And so now we can compare. Basically, this is one expression of divergence by calculating the flows, and this is divergence times the little cube. And if you just compare them, then you will find the divergence is H1, H2, H3s will then become reciprocal on the other side. And this is the first, the second, the third contribution to the divergence. And of course, once you have derived this, you can always set H1, H2, H3 equal to 1, right? To see whether this whole thing is reduced to Cartesian coordinate or not. And it does. If H1, H2, H3 is 0, then you just got dj1, dq1, or djx, dx. And the second term is djy, dy, and the third term is djz, dz. And that's it. So that is how we find the expression, the general expression of divergence in curvilinear coordinates. Okay. So that comes to the second part, the divergence. And since in YouTube Live there will be some slight delay, I'm using the standard delay. And so can any one of you just say hello or something on the chat room, so let me making sure that everything is working all right. Is that okay? Is that okay? 好，就稍稍中文插播时间，大家稍稍来讨论一下。所以到目前为止有问题吗？好，至少大家还有 hello， 就表示目前呢还非常的良好。我现在正在看着荧幕上面所有的这个黑画面，跟大家在对，这根本就是上课最佳的良方嘛。我都还知道谁上来了，谁下去了。目前串流的状况长什么样子，根本连点名都不用点名就知道有多少人来了，哎，真好。唯一不知道的就是我没有反向 camera， 所以我不知道你们到底有没有在看。你们搞不好其实只把手机就亮着，然后就开始继续睡觉了。然后这些 hello 跟没有问题跟所有东西，搞不好其实是 robot 打出来的。对，就大家的程式都很棒，这样，还打了很多表情符号给我，这样。好的，我们的中场休息时间到了，真是非常任性的直播主这样，这个自己爱休息就休息。So that's coming back to our learning materials. let me try to plug it in. I think I might need to, yeah, I probably need to charge my computer here. And it's not charging. Okay. Is this another sign telling me that I need to speed up? This is terrible. What is J here? Okay, so we have someone asking that what is J here? Well, the J is just an arbitrary vector field. It can be V as well because we are trying to calculate the divergence J. And since I want you to have some of the ideas, so I'm in particular writing it as J, but it can be arbitrary vector field because with a vector field, then we can calculate the divergence. Okay, good questions. Thank you for the meaningful questions. So then the third one is that we are going to move on to the curl. Okay, so again, as you might have seen, that the curl also have some definitions. So what exactly is a curl? Curl is the uh-oh. Okay, we are back. 所以这个就是你如果在网络上面讲一些不恰当的言论的话，你就会被绿屏了。刚才呢就被绿屏了。好，I do apologize. My computer somehow went crazy and then crashed. So I re-established everything and then saved it back. So let's move back to our learning materials again. That's the curl. So in curl, this is going to be slightly harder. So how do you really cook up a way to measure whether the field rotates or not? It turns out we need, just like Mr. Cube, that's so useful in computing the divergence. We need Miss Loop to save our date. So what is Miss Loop? Miss Loop is basically just a very simple square like this which you can orient it in different directions. And so how can we know whether a field is rotating or not, or has a tendency to rotate? It's relatively simple. You place Miss Loop there, calculate the circulations, and to see whether it's zero or not. If a field is flowing in one direction on these two sides, then this tend to rotate this way, this tend to rotate this way. They will balance each other and this whole field won't rotate, right? So that's why we are calculating the circulation. And if the circulation is not zero, then the corresponding curve is not zero. So let's then march forward to see how we can do this. By the way, there's a very beautiful relation. It's called we will prove this in general in next lectures. Okay, so here you can just imagine that how we are going to define a curve geometrically. That is, we call out a mixed loop. We calculate its circulation and divide it by the area, and we call that the curve in that particular component. And since you can orient mixed loop in different directions, right? So you get different answers of curves along that particular direction. So let's move on and see how you can do that. And so that's first calculate the circulation in the Q1, Q2 plane. That is that I'm orienting my mixed loop along the third direction. Okay. So there are 4 contributions. It's one from this, one from this, one from this, and one from this. Okay. So as inspired by the calculation in divergence, we know that we are going to compute this in pairs. So let's first compute the pair here. So for the H2 DQ2 segment, you're calculating the circulation along this direction. So you're only to pick up V2 and then times H2. And so its value at Q1 DQ1. And since you're comparing the difference between these two, it's moving in this direction. It's moving in opposite direction. That's why that you have a minus sign here. And here again, that's just H2 V2 times DQ2. So these two terms, again, at the first glance, you might think that, oh, that is 0. But of course, we know that they are not really 0, right? Because the field component here and also the scaling factor H2 here and there might be different. So we just keep it away like this. So that's the first pair. The second pair is this one here. So this is moving in this direction and this is moving in the opposite direction. So be careful here. The positive sign is the H1 and the V1 direction here. Okay, so that's the positive one. And this is negative, so that's the negative one. So it's a H1, V1, but then at slightly different Q2, right? So the lower one is at Q2, where the upper one is at Q2 plus DQ2. So once you have write this down, this is slightly easier than the divergence, because for the divergence you have 3 pairs, right? You have 6 planes, but here you basically only got 4 segments, and 4 segments corresponding to just 2 pairs, and then you can compute these 4 things. Okay, so let's see how it goes. The first one here again is nothing but partial derivative along Q1. So then you take Q1 and H2 V2 and times dQ1. And since both contain dQ2, so then you get this common factor dQ1, dQ2. And the second term, they have common factor dQ1. But look at the difference here. This term and this term. These two terms can be combined together to give you this partial derivative times dQ2. And combine dQ1 and dQ2, again, this term has dQ1, dQ2. So writing everything down, then you get this one. Again, once you got a correct answer, okay, it's the similarities and also the beauty of that sort of ensure that you got the right answer. So here you see that these two multiply together, H2V2, and then dQ1, and then this H1V1 and dQ2, and at the ends, it's just dQ1, dQ2. So everything makes sense. So basically, that is the curves along the perpendicular directions, right? Because I'm choosing Mr. Loop to be in the third direction. And so with this, we know that try to be slightly more careful because the surface here is not dQ1, dQ2, but this H1, H2 times dQ1, dQ2. Thus, finally, comparing the circulation we calculated and also compare with the expression here, we finally come to these expressions. this expression is just 1 over h1, h2. Now you know where it comes from. It's coming from the area of Miss loop and also the circulations. That's coming from two pairs of the segments. And so that is this one. Okay. So here I try to go through the logic that how you can get this, but if really want to understand this whole thing, I would really suggest you should just go over the calculation itself. Otherwise, you won't really pick it up. And once you get the third component, you can of course just generalize it to other components. And it turns out, if you just work out all the details, this curve V can be written this way. That is, you put, instead of E1, E2, E3, you put H1, E1, H2, E2, and H3, E3. That's basically A1, A2, A3s. And in the second row, you put in DQ1, DQ2, and DQ3. That is their operators. And in the third one, you put in H1, V1, H2, V2, and H3, V3. Okay? And so you multiply them all together and divide it by 1 over h1, h2, h3. And then you will get this one here. For instance, if you mark out the third one here, okay, you got this. And then because you multiply by this, and then one of the component cancel out. And so because when you got this is the h3, right? So the h3 will cancel this h3, and that's why that you are left with just 1 over h1, h2. And this expression is nothing but this expression here. So work it out. You will find it really fun. And so once you got this forms in terms of determinant, you also find the pattern is relatively simple. And so that is the curve in general called linear coordinate. Okay. So from here, I do hope that you go back and then just generalize the idea of how you change gradients, divergence, and curves. And the geometrics, that definition will actually help you a lot more so that you can actually understand its geometrical meanings and thus derive its expressions in curvilinear coordinates. Okay. And what is the interpretation of partial V and partial S? I do apologize, I'm probably loving math too much. So since some of you have asked, so let me explain a little bit. Some of you might notice that here is S and here is partial S. So this is the notation that we use in differential geometry. So the S means I'm doing a surface integral, so it defines the domain of the surface. And so partial S means that the S itself is an open surface, and then the partial S is just the boundaries of it. And of course, a surface and its corresponding boundary, the loop, is still got ambiguity, and we always use our right-hand rule, okay, to define the direction of the surface and the direction of the loop. And so that's the S and the partial S. And similarly, if you look back to divergence, then you also find this very cute expression here that you got a volume, right? And you also got partial volume. So the volume means basically just the cube itself. On the other hand, because this volume here is finite and thus is enclosed by the boundary is a closed surface. And so in shorthand notation, we will express that as partial V. And so now you can actually already see this is a very interesting correspondence. I think this is really great questions when we try to understand. If you just take it and learn it in Cartesian coordinate, you might just find that, oh, this is just a bunch of definitions and I can use inner product, outer product, and really simple. But once you try to understand its geometric meanings carefully, you found this what we call the bulk edge correspondence. That is the bulk and the boundary seems to have some non-trivial relationship between them. And that is, if you think a little bit more, that is actually the core of calculus, right? The core of calculus is that you integrate over some interval, and that is determined by the endpoints of some other function. But if this sounds too deep to you, that is fine. Don't worry. We have more lectures coming up, hopefully without the green screens in the future. Okay, and then we can talk about that more. Okay, okay, great. Thank you for the. Oh, in fact, some student has already give a preliminary answer to that. So here is the summaries, and also asks a very simple check. How can you know that whether you understand this whole thing or not? And so let me emphasize one more time. When you watch everything on the so-called YouTube live, you do not really need to take real-time notes. And the video will be there. Okay, as I explained, it will disappear for several hours because YouTube platform is organizing everything and put everything into places. It will reappear. So do not worry. So when listening or when taking these online courses here, what you need to do is really try to understand the logic behind us. And with this logic at hand, you can either just work out all the detail by yourself, or you can go back to the video and then step by step, checking whether your derivation works or not. And if both of this doesn't really get you out of the confusions, you have DAs, and of course, we have e-learn platforms. You can just post your confusion and question there, and then I will try to answer. Okay? So that's typically how the course works in the YouTube Live format. So that is the part of that. Now let's come to another part. That's the line surface volume integrals. And to be honest, this is not that difficult. So if you just draw everything together, and I'm going to explain this in Cartesian coordinate, because the line surface volume integrals in terms of general curvilinear, well, it's going to be really complicated, and I don't really want to drag you into black holes and general relativities. Yeah, since most of you are still freshmen. Okay, so I'm going to go back. So that's great. We have exciting right into the curvilinear coordinate, and now we are coming back to Cartesian coordinate, our cozy sweet home. And so the inverse operation of these vector operators are various integrals. So the first one is line integral. So what is line integral? When you perform a line integral, you need to specify which lines or which contours that you want to perform integrals. And you cut this into little segment dr, and it can be written as dx, dy, dz. So when you write it out in component, that is f dot dr, that the geometric form can be written into the component form. You just sum it up. So this should be relatively straightforward. And how useful is line integral? Oh, of course, you can find lots of line integral that we use, right? For instance, the most common one is work. And you can also find some other line integrals in electromagnetism. So I won't bore you with the physics detail here. So that is the first part. The second part is the most challenging one. That is the surface integral. So what is a surface integral? First of all, you draw out a surface, right? And take a little segment here. So it has an area, and it also has a normal direction. And typically we use right-hand side. So if the contour is using right-hand side counterclockwise, it will correspond to some directions. So that kills the ambiguity that whether the surface should be pointing in this direction and pointing in opposite direction. So in order to avoid confusions, so we always use the right-hand rule to determine the direction of the surface. Okay, so once you got that, so a surface is a vector. the total differential is just a little tiny total vector, okay? And so a vector can form in a product, for instance, with another vector field. Here, instead of using J, I'm using E, so the E stands for the electric field. So in electric field, there are many occasions we need to calculate the flux, electric flux, through some surface. And so how do we do that? Well, we put in the vector field, perform an inner product with the surface elements, and then sum them up together. Again, let me emphasize one more time, when you perform the surface integral, you need to specify which surface you are doing the calculation. Okay? So, and sometimes we will write this in this form as well. So it's E dot N and times ds. And ds can be non-trivial, the n sometimes can be even more non-trivial, and so then you don't really have a very simple dx, dy, dz component expressions. Okay, and that's why the surface integral typically is the most tricky one. And then we come to the third one. In 3 dimensions, you can also have a volume integral. For instance, you have some densities and you want to calculate the total mass or the total charge, then you would need to calculate a volume integral. So here, for instance, you have scalar field, a density, and you multiply the volume, and then it will corresponding to the mass, and you want to calculate the total mass of some things. And so then, again, please be aware that you need to specify which volume you perform these volume integrals. And in Cartesian coordinate, these volumes are the Mr. Cube. That's really trivial, right? It's nothing but dx, dy, and dt. And so then you just perform this triple integral, and then you can get the answer for the volume integral. So these are the three types of integral that I would like to introduce to you: the line integral, the surface integral, and the volume integral. So these are the inverse operation of the differentiation that we talked about before. And for instance, to give you excited, that's just a bit the Archimedes principles. So we all know this, how you describe the buoyant force. So we know if you place an object inside a liquid, it will basically, there will be two forces acting on it. The first one is the floating force. The second one is the gravitational force. And we will be concentrating on the floating force. So how does the floating force come about? Well, it's really because they're microscopically, their molecules are hitting the surfaces, right? And then creating some pressures, and this pressure in turn generate very microscopic forces, and you adding up all these forces, and then that is the floating force. That's cute, isn't it? That is really complicated. And somehow, according to Archimedes' principle, it says floating force equals the weight of expelled liquid. Wow, that's pretty cute. That is that, as I explained, this buoyant force, the floating force, is a result of surface integral. And the weight of the expelled liquid, as it turns out, that's a volume integral. And so Archimedes' principle is again just another beautiful realization of calculus. That is somehow, see, you calculate the volume integral, and its boundary is the curved surface. That then is a surface integral, and somehow they are related. And this is not surprising. This is basically everywhere that when you learn field theories, you always found this bulk boundary correspondence. Okay, even now with some topological materials. Okay, and so let's elaborate it a little bit more. You have a segment ds here, and so how can you calculate the force? We know the pressure in isotropic liquid is a scalar, so the force it generated is minus the direction of the surface times the surface and times pressure. Or in vector form, you can just say it's minus P and ds. Okay? And so let me emphasize one more time. There has been misconception saying that, oh, the pressure is small, it somehow just reacts, so you rotate the surface and the force changes accordingly. No, this is a wrong description. So in isotropic liquid, the pressure is a scalar. It's a scalar, okay? It's a scalar. And pressure in Mandarin is a really bad name. It's translated as 压力, okay? And it is really not a good name because then you might misunderstand that pressure is a vector because force is a vector. But it is not a vector. In isotropic liquid, pressure is a scalar. And a scalar multiplied with the area then give you the force. And that's why the force always follow the area. That's the origin. There's no smart force or something like that. It's just a very beautiful fact that pressure in isotropic liquid is a scalar. Okay, once you got that, we can calculate the floating force. So the floating force is just you adding up little piece of forces, and for its surface, its force is minus P times ds. Okay, so it's a surface integral. On the other hand, what is the weight of expel liquid? Well, you just take a little cube inside that. It has a little weight, right? And that little weight is density times gravitational field times dV. And you just sum it all up, and then you get the weight of the expel liquid. And that's a volume integral. So from here, you see the floating force can be expressed as a surface integral. And the weight of the expel liquid can be expressed as volume integral. And it's really, really cute that this surface integral always equals the volume integral. Okay, so for curious cat, remember this very interesting coincidence, and then we will come back and then explain why this works. So at the end of the course today, I'm going to show you one calculation. So later on, in our YouTube live, whenever you see this EX, that's an example. So I'm going to show you how you can calculate the surface as of a hemisphere. So here, I just draw a hemisphere like this one here. And so let's calculate the S of the northern hemisphere. So the vector surface S is just adding up all ds. How can we proceed? First of all, writing ds as n hat times ds. And before we already derive the spherical surface, that's the area, is a squared sine theta and d theta d phi. So we now know the area. And the direction of the area, that is also simple because it's in radial direction, right? So it's just removing the r. So this coordinate without r, this is y coordinate without r, and this is z coordinate without r. And so now you also got this expression. So once you got this, just write down the integral. Remember, ds is a vector. So the integral can be separated into I and j and k component. Okay, so it all contains the same regimes, that d theta from 0 to 2 pi over 2. That is because it's a half semi-sphere. And d phi is still going from 0 to 2 pi. So these are all the same in 3 different components. And the ds, that's a squared sine theta, that's of course all the same. And so the vector directions come from n. So in x direction, this is sine theta cosine phi. In y, that's sine theta sine phi. And then, most importantly, in z direction, that is the cosine theta. Okay? So now you write everything in terms of this. So that is great. These are all fundamental integrals. You should be able to calculate that. And I just highlight it because it is a cosine phi and no other phi dependence, and cosine phi just runs through all possible value. It integrates from 0 to 2 pi. You got 0. So great, 1, 0. This is sine phi and integrate over all d phi. You got 0 as well. Good. So you know for the hemisphere, when you try to integrate the vector surface, it does not have I component, it does not have j component. End of the stories. So you only need to calculate the k component. The k component contains a cosine theta, and sort it out a little bit, putting down a square constant here, and integrate over d phi, give you 2 pi because there's no phi dependence, and integrate over this is rather simple because you can stick cosine theta here is d sine theta, and then it's sine theta, d sine theta is just 1/2 sine square theta, plugging into the upper and lower limit, then you got 1/2. So this give you 1/2, this give you 2 pi, and then combine them together, you got pi a squared k. So this example is fundamental, and this sort of help you how to solve data. I always encourage you, when you learn something new, always try two things. Find simple and fundamental example to work it through to check whether you truly understanding this whole thing. So that's the first step. That is, learn how to compute and how to really put this into technical details. Please do not try to comprehend abstract concept by abstract concept, because most of the time you are then confused and confined by your own intellectual ceilings and with lots of twisted understanding, and you won't even notice that because that all come from your own brain. Okay, so don't do that. So step one is that try to find fundamental example, work through the details. The second one, sometimes when you do this, and if you can visualize it, that will be even better. So really, learning this applied mathematics to reasonably good levels, as long as you capture these two main spirits, you will be fine. Yeah, that's actually how I learned math. Yeah, not really just through abstract arguments. And I don't believe most mathematicians, ooh, I'm running out of batteries, but if I try to charge my computer, you might turn into green screen one more time. I hope it doesn't kill this whole YouTube live. I apologize for this technical issue. Okay, but here you know that this pi a squared k happen to be just the surface here. If you just look at the disk behind the hemisphere, then you find that this area is pi a squared, and its direction, of course, is just in the k direction. So is this a coincidence? That means that you have a hemisphere here, that's S2, and you have another one, that's the disk, that's S1, and this S1 and S2 has a common feature, that is they share the same boundaries. And it seems if two surfaces share the same boundaries, then their vector surface take the same values. And that turns out to be correct. And that's actually coming from a very simple, well, okay, I wouldn't say simple, sorry, but just make you have something to look forward to with the divergence and the Stokes theorem that we will learn in the following lectures. I think I need to end this YouTube live pretty soon. Otherwise, we will be getting the same problem again. Okay, it's not working. Okay. I guess then I would just yeah, I would just end it out. I'm sorry that yeah, my computer went crazy one more time. So the final slide, I would then just leave it as a mysterious puzzles for you to choose on. But one thing I would like you to or to discuss or try to digest, that is that why are two surfaces with the same contour integrate to the same value? Is that a coincidence in the hemisphere I just calculated, or is that really coming from something deep? Riley has a very interesting argument saying that for all closed surfaces, if you try to calculate the surface integral, it is zero. So are you convinced or not? And I got some answer, but unfortunately, so my computer apparently is running into some problem. So I'm not going to bug you at times anymore because solving this will cause a further delay. So then I will end our YouTube live today, and I do hope that you find all this materials interesting. Yeah, and I'm sorry that I cannot switch to the other learning screen at this point. Okay, so hopefully, except the oh no comment, I hope that you enjoyed the YouTube live today and you learned something new. And I will then see you on Thursdays, and I will change to another computer which wouldn't do this anymore. Bye.